Okay, so we're continuing with 4-6 on basis and dimension, and this problem is going to be a little more on the trickier side, and it does involve something from 4-3 as well. And the thing is that a lot of these problems, um, they often end up being a two-parter, where when you find the basis and the dimension, you usually have to find some kind of subspace initially, or something along those lines. So that's what this problem is. And so here's the problem. So A is this matrix, 1, negative 1, 4, negative 3. And our goal is to show that the subset W of M2C consisting of all 2 by 2 matrices that commute with A is a vector subspace of M2C. So part A is showing that every matrix that commutes with this matrix A that we have here is a subspace of 2 by 2 matrices with complex entries. And then the second part then is to find a basis for the subspace. So what do we want to do first? Well, the first thing we want to do then is to find what a matrix that commutes with A looks like, right? So what does commuting mean? Well, here's A, 1, 4, negative 1, 3. And to commute with A, we don't know what that matrix looks like, so we'll just call it A, B, C, D, right? And multiplying on the left and multiplying on the right shouldn't matter. So we get that A times our unknown matrix is equal to our unknown matrix times our matrix A, right? So we set up this equation, and now we just have to actually multiply both sides out. So what do we get? We get A minus C, and then B minus D, and then 4A minus 3C, 4B minus 3D. Okay. The next part on the right hand side, yeah, and so we get A plus 4B, negative A minus 3B, C plus 4D, negative C minus 3D. Alright, so what do we want to do? Well, because these two matrices have to be equal to each other, since we need to find the matrix that commutes with 1, negative 1, 4, negative 3, this entry has to equal the top left entry of the right hand side. The top right entry has to equal the top right entry, and bottom left has to equal bottom left, bottom right has to equal bottom right. Okay, so we get this system of equations. We get A minus C is equal to A plus 4B. B minus D is equal to negative A minus 3B. 4A minus 3C is equal to C plus 4D. And 4B minus 3D is equal to negative C minus 3D. Okay? And now, what do we want to do? Well, we kind of want to actually solve this as a system of equations. So if we subtract everything over to one side, we actually get, if I actually move this over to the right hand side, I actually get 4B plus C is equal to 0. Okay? And then here, I'll actually move stuff from this side over here, so we have more positive numbers to deal with. I get A plus 4B minus D is equal to 0. This term here will move everything over to the left. I get negative 4A plus 4C plus 4D is equal to 0. And then this last term, hey, hold on, if I move everything over to the left, I actually end up with 4B plus C is equal to 0. So I actually have 3 equations, 4 unknowns here. So what can we do? Well, nothing really, but we can solve for whatever we can. So if we make this into a matrix, right, this is actually 0, 4, 1, 0. Okay, this row goes here, right? And then I get 1, 4, 0, negative 1, and then I get negative 4, 4C, so this is 0, 4, 4, and 0, 4, 1, 0. Okay, and what is this equal to? Well, this is actually just equal to a bunch of zeros on the right-hand side of an augmented matrix. Okay, and let's solve this system of equations then. What do I get? Well, I get 1, 4, 0, negative 1, 0, because why not? I will switch these two rows. 0, 4, 1, 0, negative 4, 0, 4, 4. And then this last row I'm just going to zero out right away because it's the same thing as the first row. Okay? And then, where do I go from here? Well, let's zero out this guy. So I get 1, 4, 1, 0. 1, 4, 0, negative 1. 0, 4, 1, 0. And then I get 0, 4, 0, 16, 4, 0. And that looks like I can zero out the third row now because it's just a multiple of the second row. And here we go. This is our system, right? So what does this mean? Well, here's our pivots. And this means I have two free variables corresponding to C and D. Okay? Right? Because notice, what are we doing? We're actually technically taking this matrix here, and we're trying to take this matrix, not the augmented part, but just this part right here, and we're multiplying it by a vector A, B, C, D, right? So everything in the first column gets multiplied by A, everything in the second column gets multiplied by B, right? So we take this purple guy, and essentially that goes there, right? And we want this to equal 0. So you see that C and D are free columns. So what we do now is that we let C equal C, right? And from row 2, I see that 4B plus C is equal to 0. So that means what? That means B is equal to negative 1/4 C, right? And then, okay, does that create anything in row 2? In row 1, it doesn't, because there's no the equation in row 1 doesn't contain C, right? It's 0 for the C value. So, okay. What else can we do? Then I want to let D equal to D, right? And then over here in row 2, our D value is 0, so we can't consider that equation. And then I have this equation, A plus 4B minus D is equal to 0. Well, what is B? Well, B is equal to negative 1/4 C, right? So this is actually A plus 4 times negative 1/4 C minus D is equal to 0. And A ends up equaling D plus B, or B plus D. Or C plus? C plus D. Okay. So A ends up being C plus D, and so now we have B in terms of our free variables, and we have C in terms of our free variables, which are C and D, right? Because those were the ones without pivots. And now let's go back to our original matrix of unknowns here, A, B, C, D, and we'll realize that A, B, C, D actually equals A plus D, or C plus D, negative 1/4 C, C, D, right? So this is the matrix that commutes with the matrix A right here, right? So this is the type of matrix that it looks like. And so what do we have to do? Well, we have to prove that this is a vector space, and or a subspace. And how do we do that? Well, remember, subspace, the first thing we want to do is closed under addition. And, well, I mean, if you add two matrices that look like this, you're going to get something back that looks like that, right? Because let's say you have C1 D plus D1, C1 D1, negative 1/4 C1, and you add it to C2 plus D2, C2 D2, negative 1/4 C2. Well, this resulting matrix is just C1 plus C2 plus D1 plus D2, and then this is C1 plus C2, this is D1 plus D2, and this is negative 1/4 C1 minus 1/4 C2. If I call this like C, if C1 plus C2 is equal to, let's say, C hat, right, and then D1 plus D2 is equal to D hat, what do I get? Well, then this becomes C hat plus D hat, and this becomes negative 1/4 times essentially C1 plus C2, right, which is then negative 1/4 C hat. So yeah, so then our entries in our matrix actually equal C hat plus D hat, negative 1/4 C hat, D hat. Okay, which is exactly in the form of this guy up here. So this is in the form of the commutative matrix. So yeah, that works, right? Okay, what's next? Well, it's closed under scalar multiplication, and this one's pretty much a no-brainer. Like, if you multiply a scalar through every entry, like if you multiply this guy by a scalar k, then every entry gets multiplied by k, but that is still in the form, right? The ratios still hold. Yeah, so this one's really easy to show. C1 plus D, or just C plus D, C, D, negative 1/4 C, right? And this is equal to then K, C plus D, negative K over 4C, KC, KD, and then you make a similar substitution where you let KC, you let this be, let's use a different color. You let this be C bar, and you let this be D bar, and yeah, I mean, you get C bar plus D bar, negative 1/4 C bar, D bar, which is also in the form of this guy up here. Zoom out, right? So this matrix down here is, it's in the form of this guy that commutes with A. All right, so it's closed under addition. The second part is closed under scalar mult, and so the third part then is to show that it contains 0. Well, if C equals 0 and D equals 0, then we get 0, 0, 0, 0, which is the 0 matrix. And so, yeah, it contains a 0 matrix, so it's a subspace. Okay, that was a lot of work, but all we did was show that the matrix that commutes with 1, negative 1, 4, negative 3, every matrix that commutes with this matrix up here is forms a subspace of 2x2 matrices. So now what we want to do then, part B, is to find a basis for W, right? And W just means all matrices that have this form right here. Okay, let's erase this K here. So this W contains every matrix, every 2x2 matrix with complex entries that looks like this, right? And so what do we have? So W, so a matrix in W looks like C, D, C plus D, and negative 1/4 C. So, like we did with finding bases, we're going to extract each. Element by itself. Okay. And how do we do that? Well, we extract each unknown out. So this is equal to C times 1, negative 1/4, 1, 0, plus D times 1, 0, 0, 1. Okay? And this is our basis. So our basis for W contains two matrices, which are 1, negative 1/4, 1, 0, and 1, 0, 0, 1. and we're done, right? Because this is the basis for W. Why is the basis for W? Well, it obviously spans because that's how we created this matrix here. It spans because C and D are going to be any scalar, and then when you do that, and when you choose the scalars, they're going to look like this matrix here. Okay, so it spans. And why are they linearly independent? Well, it's because they're not multiples of one another, right? So when you have two elements, as long as they're not scalar multiples of each other, then they're going to be linearly independent. And also, right, there's a 0, there's a 0. These guys are not 0, so you can't make one of the matrices into the other one just by creating a linear combination with itself, right? So, yeah, these guys are linearly independent, and so the dimension is going to be 2, and the dimension of subspace is 2. This is what the subspace looks like. This is what the green here is what a matrix in the subspace looks like. This right here is going to be the basis for W, and the dimension of W is 2. And so, yeah, so this problem, really the hard part was finding what the subspace was. But once you have the subspace, you essentially have like the general form then, and then you want to go and create a basis for it by, again, extracting out each independent unknown and having that unknown multiply some matrix, right? And I know both these examples we've done have involved matrices. Again, bases don't just apply to matrices. They apply to polynomials, they apply to solutions to differential equations, they apply to vectors. So, again, in recitation and in my lectures, I'll talk about these things. But, again, if you're watching this and I'm not TAing 240 this semester or something, understand that, right, bases can apply to anything. And again, I mentioned in the first video in this section, go look at the old videos from section 4.6 that I have. Go look at the problem for 4.4. And what else? Oh yeah, the notes I think are okay on this section. So I have the 240 notes. They might be still incomplete, but those are fine. And yeah, I would definitely look at those when learning about basis, because again, this is one of the most important things that you'll learn in Math 240.